Hey guys, my apologies again for the cancellation of class so last minute. Got the flu bug that's been going around everywhere, so I'm going to try to keep up with a video lecture for you guys. Hopefully you saw the review video lecture. If not, no worries, it's always available for you. So last Wednesday where we left off is we were talking about acids and bases. Now acids we should remember that some acid is something that donates protons. Now, we should also remember that when we're thinking about acids, we have this so-called proton, and we can't actually see it in solution. What we actually see is this crazy character known as hydronium, H3O+. Now, when I think about an acid, say HA again, and I look at this hydronium, it looks a whole lot like water. We talked about the Arrhenius theory, which talked about how protons, or H+, is being dissociated. But we talked also about the BL theory, the Bronsted-Lowry theory, that told us that, well, not really. It's more just about donating protons to something like water. Now, when we have water, we form H3O+ in solution when I add some acid. And again, I'll put this A- over here. When I have a base reacting with water, some base, I'll call it B, acids donate protons while bases accept protons. I form Hb plus and I form OH minus. So I should remember that in solution, if I add an acid, I will always form H3O+. If I add a base to water, I will always form hydroxide OH minus. Again, I add an acid to water and I form H3O+. I add a base to water and I form hydroxide. No matter what acid, no matter what base, I will always form H3O+ or OH-. Now, we talked a little bit about a couple of reactions that we saw. The examples that we saw were these ones. Now, the question asks, which of the following are acid-base reactions? We should remember there are three things that I need to have an acid-base reaction. First, I need an acid. Second, I need a base. And third, I need a transfer of protons. So the first reaction given was, well, 2NaClO3. And then in the end, I get 2NaCl, whatever that stuff is, and 3O2. Now, this reaction, to be considered an acid-base reaction, I should be able to recognize an acid, a base, and I should be able to recognize a transfer of protons. So here, I remember that a proton is H+. Do we even see hydrogen anywhere in this reaction? The answer should be no. So this reaction cannot possibly be an acid-base reaction. Same with the second reaction where I have AlBr3, I have aluminum, I have bromine, and I have chlorine. And again, I see no protons anywhere, so this could not possibly be an acid-base reaction. Now we skip to the last one. H2SO4 plus H2O producing H3O plus and HSO4, oopsies, minus. So I look at this reaction now, and again, the three things that I should be able to determine is, well, do I have an acid, do I have a base, and am I transferring protons? So I look at this guy here. I look from beginning to end. I see that that HSO4 character looks most like H2SO4. If I look at this, it looks like, well, what changed? It looks like I lost an H+. Okay, I look at my other player, water. Now water started as H2O and it kind of looks like in the end it turned into H3O+. This is the character that looks most like water. Now to go from H2O to H3O+, it looks like I had to gain an H+. Now if I'm able to see someone losing an H+, someone gaining an H+, that means that I must have a transfer, again, of a proton. A transfer of a proton means that I should be able to identify who my acid is and who my base is. Again, my acid donates. Acid donates. Again, losing is just another word for donating, so I would classify this guy as my acid. Meanwhile, water would act as my base. Now we should be thinking, well, shouldn't I try to say which one is an acid and base on this side? No. Do not try to write acid and base on the product side. We say that my acid is someone who donates a proton. My base is someone who accepts a proton. So when we are writing down who is my acid, who is my base, I should only be writing it in my reactant side, so on the left. All right, so now the next example given, 6Na plus 6 H2O, producing 6 sodium hydroxide and 3 H2. Now looking at this, I'm thinking, oh, I actually see some transfers of protons and I see a whole bunch of stuff happening, so yeah, totally acid-base. But again, the three things we should be able to see in an acid-base reaction is an acid, a base, and a transfer of protons, and only protons. We should not be transferring anything else but protons. Whether we transfer 1 or 20 protons, the only thing that should be being transferred is H+. Now, I look at this reaction, I'm like, okay, so let's first start with this guy here. What does he most look like in the end? Well, I look at the end, and I'm either with sodium hydroxide or hydrogen, and it kind of looks like sodium, looks most like sodium hydroxide, I guess, in the end, if I'm going to say what we started as and what we ended as. Now, if I look and see sodium, okay, so it looks like it gained an H, but it also looks like it gained an O, so I kind of gained OH is what I gained here. It doesn't look like I gained any charge at all. Okay, so let's just say for the sake of argument, we're going to call that, I don't know, a base. I gained something, right? So I'm just going to call it a base just for funsies. Now water. I look at water and I've already classified this thing as coming from sodium, so I guess water had to turn into H2, and it kind of looks like I lost an oxygen. Now, I guess an acid, maybe something that loses or donates something. Okay, now looking at this, is this a transfer of a proton? Does this look like someone is donating a proton, someone is accepting a proton? If I look at what I classified as my base, someone who's accepting something, I didn't accept a proton, I accepted OH. Now, that's not a base. A base is someone who accepts protons. So that doesn't really work very well. Now my water is supposed to be my acid, meaning it donates. Acid donates protons, but it looks like it donated oxygen, and it's just all kinds of crazy. So I would say that this right here is not an acid-base reaction. Again, because an acid-base reaction requires an acid, a base, and a transfer of protons. Now, if I look at the next slide is telling you to identify the acid and the base in the following reactions. So I look at these reactions and I think, okay, I see a whole bunch of different players here, and I need to identify who my acid is, reminding yourself that acid donates protons and bases accept protons. So I look. Let's write down the second one first. NaOH plus HCl. Now, before I write the products, we should be able to, at this point, start to recognize, well, sodium hydroxide, it has a hydrogen, it is capable of donating a proton, but I should recognize this already as a base. I should recognize this already as a base. HCl, I should know. HCl, hydrochloric acid, I should be very familiar with that, is an acid. Now, before I write the products, we're going to move on to a different one. We will come back to that one in a second. So, one of them, H2SO4 plus H2O, this is one that we dealt with previously, gives me H3O plus and HSO4 minus. So looking at this reaction, again, I should be able to determine, based on how I started and how I end, what happened to me. Now, if I look here, it kind of looks like H2SO4 going to HSO4 minus. It looks like I donated or lost an H+. That should make me an acid if I donated an H+. Now, I look at water. Water seemed to have gained an H+. Water went from H2O to H3O+. H2O to H3O with a positive charge, and I should be thinking, well, someone who gains a proton would be a base. Now, this is kind of interesting. Water. We've seen, I thought water was supposed to be neutral. We think of water as neutral. Uh-oh, I'm seeing water acting as a base. That's kind of interesting. Okay, so I've labeled my acid and I've labeled my base. I'm feeling good. Now, the last one on here, let's go and do this one actually, the one that looks very similar. H2SO4 plus H2O plus 2H2O, in fact, producing 2H3O plus SO4 2 minus. Now, if I look at this, H2O again Looks like it starts here and ends as H3O+. Now, kind of weird that there's two of them. Some kind of red flag should be going off in our mind. But I'm seeing that water starts as H2O and ends as H3O+. Again, water gained a proton from beginning to end, meaning I would label water as a base. No matter how much it gained a proton. There's two waters and each of them gained one single proton, so I should be thinking water's acting as a base. Okay, now I look at my other player here, and I see H2SO4 turning into SO4 2-. When I see this, I see a loss of protons. In this case, I actually see a loss of 2 protons. So I see a loss of 2 protons. Now I didn't lose anything else, so I'm going to call this my acid who donated 2 protons. Now, when I donated 2 protons here, this is actually called a polyprotic acid. H2SO4 is a polyprotic acid. Now, if you break that down, poly meaning many, protic having to do with protons, many protons. H2SO4 specifically has 2 protons that it could potentially donate. Okay, so my polyprotic acid now, again, I can write 2 different equations and both of these would be correct. The first one, where I had H2SO4 only donating 1 proton to water, my second equation written, where it is donating both of its protons to 2 different waters. Now, one thing to note here is that I never wrote the equation H2SO4 plus water produces SO4 2- and H4O 2+. This H4O 2+ does not exist. So, for this to donate 2 protons, what I will need is 2 waters, and I'll draw them both out. 2 waters. Each of these waters will gain 1 proton, so then in the end, I end up with one of them as H3O+, and another one of them as H3O+. I will not form H4O+. Please note, there is no such thing as H4O 2+. I will always form hydronium, H3O+. Alright, so that is it for those 2 trying problems that we worked on a little bit last week. Hopefully you guys have a little better idea of them now, and I will start on the next video.